So to begin 7.3, I would give you this as a warm-up. I would ask you to use the Laplace Transform's definition, the definition of Laplace Transform, to evaluate the Laplace Transform of this product of e to the at times t squared. A is just a constant here. You will get that this only converges for certain values. I'm not worried about that so much as building a formula for this type of a product. I also would like for you to do that for e to the at times cosine of kt. Now I want to remind you as you do that, L of the Laplace transform of t squared, of course, is 2 over s cubed. The Laplace transform of cosine of kt is, of course, s over s squared plus k squared. What I'm trying to do here is help you understand one of the formulas that we'll be discussing in this section. So pause the video and try that on your own. Once you have spent some time doing that, then you should have that using the definition, as long as s is greater than a, then the integral will converge to 2 over this quantity s minus a cubed. You'll notice that the e to the at, in the denominator here we have an s minus a, so this was quite similar to the Laplace transform of t squared, which was 2 over s cubed, but now we have a composition with the function f of s is equal to s minus a, and so I want you to notice that like similarity between these two. The Laplace transform of cosine, this is here just to remind you, I ask you to take the Laplace transform of this product. You will notice that you might need to rewrite your work slightly, and this integral, the indefinite integral, does only converge for s greater than a, but if you'll simplify your solution, you should probably have this right here. You should have the quantity s minus a all over that same quantity squared plus k squared. Now, look at the similarities between these two. Cosine of kt would have been this, e to the at cosine of kt. Is that function, f of x here, f of s, is what I meant to say, the Laplace transform of that function, it's composed with the function f of s is equal to s minus a. So we actually had that same pattern between both of those, and we could certainly do more of these. Where I'm going with this is we're actually going to look at a couple translation theorems that appear in 7.3 that could help you when evaluating your differential equations using Laplace transforms. So the first translation theorem. If you already know the Laplace transform of a function, so we already have built up some properties where we know how to take the Laplace transform of polynomials, trigonometric functions, exponentials. We already know the Laplace transforms of all of those. And so, if you already know that Laplace transform, then we are able to use a translation if your function has this form. So if you have already known the Laplace transform of a function, and you take the Laplace transform of e to the at, the product of an exponential with that function, then fortunately, you will just have the Laplace transform of f of t evaluated at s minus a, so composed with the function f of s is equal to s minus a. This is another notation for writing that, so the Laplace transform of that product is equal to the Laplace transform of f of t, where you substitute s for s minus a. In this example that I had you all work, here is your Laplace transform that fits this setup. Since I know the Laplace transform of t squared is 2 over s cubed, then to find the complete Laplace transform, I'm simply taking the Laplace transform of t squared, and I will substitute s minus a in for s, so that I get 2 over s minus a quantity cubed. Similarly for the Laplace transform of the product with cosine, because I know the Laplace transform of cosine, which is given here, then I will substitute for all of the s's, s minus a, using that composition, and this is what we noticed from our warm-up slide. The inverse form is to say that if you need to evaluate the inverse Laplace transform of a function in terms of s, and you can write that expression completely in terms of s minus a, then the first translation theorem allows us to simply substitute s for s minus a, and you can evaluate, so using the inverse Laplace tables, you can recover your original function the translation will appear here as the product times e to the at. Let me give you an example. Down here you'll notice I have the inverse Laplace transform of this quantity. Well, fortunately, that looks quite similar to 5 over something squared, so we've rewritten it as 5 over s squared. Because 5 over s squared is the inverse of this quantity is simply 5t, then you'll notice here I have 5t times e to the 3t because of that composition. After you feel comfortable with the first translation theorem, another idea that appears in this section is called the Heaviside function. So the unit step function, I think of this as our flashlight function, or I'm sorry, as our light switch function. So Heaviside, I actually left a picture of here. Heaviside is named after the mathematician, but what this function does, so we often use a u here, you'll notice, and we have a function in terms of t. It is piecewise. So this function is 0 on the interval from 0. We are only using positive values for t here. So this function is completely 0 up until whatever a is, and when t hits a, when it's equal to or greater than a, then the unit step function is equal to 1. So it's either equal to 0 or 1. And if you think about a light switch, if it's turned off, you're sending no power. If it's turned on, then you are sending the electric current to light, to create energy, to send energy to that light. And so the Heaviside function really reminds me of a light switch. Another example of this, if I were to take a function, f of t is equal to sine, you should be familiar with the graph of sine, and if I were to take that and multiply it by the unit step function, evaluated here, you'll notice a is 2 pi. Well, again, the light switch, so if t is less than 2 pi, then this function is completely 0. So sine will completely be turned off. No energy will go to it until t is equal to 2 pi. Now remember, 2 pi is about 6.28, so you'll notice the function suddenly turns on, and now we have the sine curve. So this function g of t is graphed here between 0 and 2 pi. Because of it's multiplied by the unit step function, it will be completely 0. No power will be going to it. As soon as t is equal to or greater than 2 pi, we do get that function, sine of t. And so the graph, you notice, is graphed here. To discuss how this works a little bit better, so a product f of t times a unit step function will be exactly what I just had graphed. This function will only begin to appear, it will be equal to 0 until t is equal to 0. And then as soon as t is greater than or equal to 0, you will have the graph of the function. Now the graph that I actually showed you was for a equals 2 pi. So here a would be 0, here a would be 2 pi. So the function turned on, so it began graphing at 2 pi. Now, if we think about this third line, this is the unit step function, which is identically 0 or 1, and that transition is at 0. But if we graph f of t minus a, well, from college algebra, that is a translation of the function f of t, and it shifts to the right a. So this function still turns on or off depending at the value around 0, but this graph of f will translate. Now putting that together, this is the idea we're trying to get to. If we had a translation of f, so f has moved to the right a, and the unit step function turns on at a, it sends power to f at a, then this represents, this product represents the graph where f of t has been shifted and begins at t equals a, at t equal to a. So we have a couple examples. This example down in the left-hand corner for sine, so the sine graph is turned on at 0.7 is what will happen here. If sine were not multiplied by this, you would have a full sine graph, but because you're taking sine times the unit step function, you're excluding everything where t is less than 0.7. For the second graph, the graph of sine has shifted right 0.7 units. Because it's multiplied by the unit step function, it does turn on at 0 here. You'll notice a is equal to 0. And so we have the graph of sine translated, and it starts graphing at 0. Before that, it's identically 0. The reason I'm talking about this, well, we have a second translation theorem and we're building up to it, so I want to give you an idea of where we're headed. If I have a Laplace transform of the product we were just discussing, so a function that has translated to the right a and the unit step function, which sends power to f at t equals a. The Laplace transform using the definition would be as shown here. So here is your function times e to the negative st. Now the unit step function is either 0 or a. So you'll notice what we did here. If the unit step function is 0, we don't need to worry about integrating that part because the area would be 0, nothing. So I've started the integral at a because that's the only place where we're actually going to have area that's non-zero. Given that expression, we're going to make a substitution. So you'll notice on the next line, we've substituted tau equals t minus a, just introducing a new variable. It's linear, so not much I have to do for the substitution. I'll have f of tau is equal to e to the, I did have negative st, and I need to have, I can't change that, and so you'll notice what we did is we solved for t, plugged in tau plus a, so that these expressions are the same. I simply made a linear substitution, not a big deal. On the next line, because of that substitution, you'll notice you had a constant e to the negative sa, which you are able to factor out. It doesn't rely on tau. When you do that, on this part right here, on this right side, you now have the definition of the Laplace transform of f of tau, which is capital F of s, times this constant e to the negative as. What I'm doing here is showing you that for a product in this form, so you have a function times a unit step function and both are evaluated at t minus a, then the Laplace transform of that is simply e to the negative as times the Laplace transform of f of t. This is called the second translation theorem. There are a few more examples in the book. Keep in mind that it's very important to remember you do have to write that entire expression, the entire product, in terms of t minus a, which is where the tricky part will come in. Okay, in 7.3 I'm going to provide a homework assignment on Google Classroom. This was an old assignment. Please don't work all of those, but what I give you will be part of those. So I'm trying to make this video short and sweet. You'll do some of the problems from 7.3 using these new translation theorems and the unit step function. Best of luck.